Okay, so welcome. I'm going to introduce this topic of these what have now become known as product structure theorems. These are fairly new things. This picture here is was taken about 10 minutes after, I guess, the first one of these things was discovered, although we weren't really aware at the time that that this theorem would be as useful as it turned out to be. So I'll first give some informal statement of the product structure theorem and some motivation as to why it's possibly a useful thing. There'll be lots of applications later in other talks. Then I'll give the formal statement of the theorem, talk a little bit about where it came from and what the proof looks like. And I'll also mention all the generalizations and variants to things that go beyond planar graphs. And then I will just list some of the applications, and the other talks in this mini symposium will be about many of those applications. Okay, so if you made a list of the graph classes that you know, or if you went and looked up a big list of graph classes, and you tried to order them in terms of how simple or how complicated they are, so starting with the simplest ones first, you might end up with some sublist that looks like this. Somewhere near the beginning of the list, you would find paths. They're pretty simple graphs. Also near the beginning is trees, and a little further down, there's probably some things in between. You would find graphs of bounded tree width, or k trees for a constant k. I'll talk a little bit about what tree width is for those who don't know, but it's not critical for this this talk. Then there'd probably be lots of stuff before you eventually got to planar graphs. A little bit more stuff before you got to proper minor closed families of graphs, and lots more stuff before you got to the class of all graphs. So all graphs being somehow the richest set. And what do I mean by complexity here? Well, nothing formal. I just mean if you ask a question about graphs in this class, how hard is it to answer that question? And so for the most part, it kind of behaves like this. Okay, so given that planar graphs are fairly far down the list, you might ask, well, is there a way to deal with them, or some nice way to deal with them? And since this is a talk about product structure, the question I would like to talk about is, can we factor a planar graph into simpler graphs? So what does that mean? Well, I'll get really formal shortly, but the answer is yes. If you give me any planar graph, then I can factor it in the following sense, that I can give you a graph that has small tree width, h, and a path, and your graph, your planar graph, is contained in the product of those two simple things. So remember, this paths and graphs of small tree width were somehow up near the top of our list among the simplest things, and planar graphs are pretty far down. So the picture looks like this. We'll see this kind of equation a lot. G is a subgraph of h times p. In this example here, h is a graph of very small tree width. It's a tree, so it has tree width 1. That is this binary tree that you see here, and p is this path with 1, 2, 3, 4, 5 vertices in it. And there's this strong product operator. I'll talk about the definition of that in a second, but if I were to expand that now, that's the graph that you get, and you probably don't necessarily see it from this picture, but that graph on the left is actually a subgraph of that graph on the right. Okay, so a couple of things, notions in here. Tree width is one of them, I'll talk about in a second, and the strong product. I'll define both of those things Okay, so for tree width, probably many of you know the definition. Those of you who don't or haven't seen it before, I'll give it, but I'd like you to keep in mind that actually for the rest of the afternoon, you can get by without even knowing the definition, except to understand that graphs of small tree width are fairly simple, well understood in many ways, and that's the critical thing. So a tree decomposition of a graph is something you get by starting with a tree and taking each vertex in your graph and assigning it to a subtree of your tree in such a way that if two vertices are adjacent in your original graph, then their subtrees should intersect. So for example, the vertex G in this graph and the vertex E in this graph intersect, or sorry, they're adjacent, and therefore the subtree of G, which is this purple path, should intersect the subtree of E, which is this bluish, light blue path. And indeed they do. So when you have such a tree decomposition, the vertices of that decomposition, each one of them somehow, so each vertex of your tree has a collection of graph vertices inside of it. So we call these vertices of this tree bags. And the width of your tree decomposition is the size of the largest bag minus 1. If we look at this tree decomposition, we have all the bags have size 3. So the largest bag has size 3. And so the width of this decomposition is 2. And the tree width of your graph is you have to minimize the width of the tree decomposition over all possible tree decompositions of your graph. Computing tree width is not easy, even when it's small. It can be done quickly in theory, but not necessarily in practice. Okay, so that's the definition of tree width. Okay, so the other thing that you need to know about is the strong graph product. So if I take two graphs A and B and take their strong product, I get a graph whose vertex set is the Cartesian product of A and B. And the way I think of it is I will see many copies of A, in fact, one copy for each vertex of B. So for example, in this picture, I see many copies of the tree. These are the black horizontal edges. And I also see many copies of the path, B. These are the vertical paths in this graph, also in black. And not only that, but I see these diagonal edges, which you get when the corresponding vertices are adjacent both in A and in B. So for example, in the tree, the second, so this vertex, I hope you can see my cursor, and this vertex are adjacent in the tree, and this vertex are adjacent in the path, and so you get this red diagonal edge that joins those two things. All right, so now would be a time to ask a question if you have one about this. Good. And in this talk, we will see pictures like this frequently, in particular where the second thing in this product is a path. And we'll see that actually for the rest of the afternoon. Okay, so the theorem more formally is that for every planar graph G, there exists a planar graph H of tree width at most 8, and a path such that G is a subgraph of H times that path. And the multiplication there is the strong product. And you've seen this example. This planar graph is actually a subgraph of these two very simple things, a tree and a path. All right, good to know, but question is, well, why? Why do we care? Well, H in this product is a simple graph, a graph of tree width at most 8. And that means that many problems, in particular, many kinds of coloring problems, many algorithmic problems, sort of lots of things end up being easy on graphs of small tree width. And sometimes, in fact, a lot of the time, if I have a solution for the graph H, extending that to H times a path is not such a difficult task. Right? It's, I mean, we'll see the various examples of when this happens, but sometimes it's easy. And actually, it turns out to be easy enough that this is the critical thing in a solution to a number of sort of long-standing problems. So for example, the Q number of planar graphs we now know is a constant only because of this technique. Non-repetitive coloring of planar graphs. We now also know planar graphs can be non-repetitively colored with a constant number of colors using exactly this technique. The best bounds right now for p-centered coloring of planar graphs, the best bounds for L vertex ranking of planar graphs, and currently the best, at least in fact, asymptotically optimal adjacency labeling schemes for planar graphs come from this technique. And this last one is in a slightly different color because I think that that one falls sort of outside the realm of extending the solution from H to H times P being easy. That was a more involved extension. Okay, so a little bit about where this proof comes from and what it looks like. So it's actually it's based on a theorem from approximately that was a year older by Polipchuk and Sieberts. They were studying p-centered coloring, and they proved something really nice that one of us, Gwenaël Joret, felt is so nice it must have more applications than what it had been used for at that time. So they showed that if you give me any triangulation, and for the kinds of problems that we're studying today, mostly having your planar graph be maximal planar, so meaning that it's a triangulation, only makes the problems harder. So they showed that you can partition the vertices of a triangulation into a collection of paths, and not just paths, but actual shortest paths. So each subset in your partition induces a shortest path in your graph between its endpoints. And if you take each of those subsets and you contract them, so you identify all of those vertices in the subset, then that thing is called the quotient graph, denoted by H, and it has tree width at most 8. So in this picture, you can see it. The partition has two sets of size 2. There's a sort of red one, a purple one, a set of size 4, and then all the rest are singleton sets. And when I do the contraction, if I didn't miss anything when I was making this figure, this is the graph that you get on the right. And I'm certain this one has tree width at most 8, but the theorem is that for every planar graph, there is such a partition of these things. Okay. Beautiful theorem, and actually with a beautiful proof that I will just talk very briefly about. So everything that I'm going to talk about next essentially stems from this theorem. In fact, it's small changes. So I'll write another theorem that looks similar, starts the same, except in this theorem, you have a planar triangulation, G, just like before, but you've also got a breadth-first spanning tree of G. So that means it's a shortest path tree. You pick a vertex in your graph, you make that the root, and you take a shortest path tree from that vertex. So the layers of that tree, the depth of a node in that tree is just its distance from the root. Then you can partition the vertices of the graph so that each part of the partition is a vertical path in T. So what's a vertical path? That's just a path from some node in T to one of its ancestors. So vertical because we think of it as going up only towards the root. It doesn't go up and then back down. So you get a vertical path in T. And notice vertical paths in T are shortest paths in the graph. So that's like the previous theorem, but now we're very specific about where these paths come from. They're these vertical paths in T. And the second part is exactly as before. If I contract these things, then in the quotient graph, H, that when I do this contraction, I get a graph of tree width at most 8. So it looks a lot like the previous theorem. And indeed, the proof is almost the same. The only difference is that those geodesics, which were somehow unspecified in the previous theorem where those geodesics came from, these ones we know where they come from. They're all vertical paths in a fixed breadth-first spanning tree. And now, what may not be obvious is that theorem implies the product structure theorem that I mentioned earlier. So let's think about why that's the case. So you give me a triangulation, or you give me a planar graph and then augment it into a triangulation. You take your favorite breadth-first spanning tree of your graph. So pick any vertex you want and any breadth-first spanning tree rooted at that vertex. You apply the theorem that I just mentioned. Okay? So that gives you this collection of vertical paths that partition the vertices of your graph, and contract that to get the graph H. So far, there's nothing in here about products and product structure, but let's look at what happens if we take H now and we multiply it by a path. How long of a path? Well, we'll take a path whose length is equal to the height of the tree. So the longest path in the tree. In this case, the longest path has 1, 2, 3, 4 vertices. So we do that multiplication, and this is what we get. Okay. So the claim now is that this graph on the left is a subgraph of this graph on the right. That's the product structure theorem, right? H is a graph of tree width at most 8. P is a path. So where is this graph on the left hiding inside this graph on the right? Well, we can actually read that off from this partition here. So look at each part of your partition. So in this case, there's this long part that has nodes of depth 0, 1, 2, 3, and 4. So that path will map onto the corresponding node in the contracted graph. And in fact, it'll map onto nodes at levels 0, 1, 2, 3, and 4. This blue piece of the partition only has one thing in it. It's a node of depth 1. So it maps onto the corresponding node of depth 1 in the product. Same thing with the orange one, same thing with the green one. This purple path with 2 vertices at depth 1 and 2 maps onto these corresponding vertices at depth 1 and 2. The orange one goes here, and the pink one goes here. And now just check the definitions carefully, and you'll realize that if 2 vertices are adjacent in G, then their corresponding vertices are adjacent in H times P. So those two theorems are equivalent. And what does the proof of that? So that's called the layered H partition theorem, or that's what I'm calling it today. What does the proof of it look like? Well, it uses a nice proof technique, which is just to copy someone else's proof and change the parts that the words that you want to be what you want them to be. So you take the proof that was in this original paper of Pilipchuk and Zieberts, except where that paper says for a particular, so that proof involves, it's an inductive proof that each inductive step has a cycle, and you're looking at the subgraph inside that cycle, and there's parts in there where they say for a particular vertex, you take a shortest path from that vertex to the cycle. So wherever that is written in their proof, you write, you take a shortest path, not in the graph from that vertex to the cycle, but the shortest path in T from that vertex to the cycle. So don't take an arbitrary shortest path from that vertex to the closest vertex of the cycle. Instead, just walk to the root of T, which will actually be outside the cycle by construction, until you hit the boundary of the cycle. That's the path that you use in place of the one that they were using. And then check all the details and check that everything still works. Okay. So a couple of other versions of this and generalizations. So another version that falls out exactly from this proof is instead of talking about H having tree width 8, if you really want a graph of very small tree width, you can get this theorem that says not only, so G is a subgraph of H, where H has tree width 3, but then you have to multiply by a path and a triangle. This turns out to be useful in some applications. Okay, so Anna asks what was due to Tut on slide 12. I once saw a talk by Tut in which he talked about one of his favorite methods for proving theorems, and his method was exactly that. The example that he gave was changing four-connected triangulation to four-connected planar graph everywhere in someone else's proof, and then checking carefully that the proof still works. Yes, so you have this other version where H has smaller tree width, 3, which is useful. And in particular, and one of the things you will see today, the fact that H is planar and has tree width 3 makes it really special. That is another name for that. It's a graph of simple tree width 3. Okay. There's an algorithmic version of this. So if you give me the triangulation, I can find this decomposition in n log n of n log n time. There's even source code for it if you want to download it and try it out. And there are a number of generalizations, including to graphs of bounded genus, and more generally than that, apex minor free graphs. That's in the original paper. If you give me a bounded degree graph from a proper minor closed family, then that also has one of these product structure theorems. And k-planar graphs. So these are graphs that can be drawn in the plane where each edge only has at most k crossings for constant k. And in fact, even if you can draw them on a surface of small genus, it's true. The only thing that changes in these theorems is that the tree width of H gets bigger depending on exactly what you're looking at. So it's not always 8. All right, so that's everything I wanted to say about that. Just a look at what's coming up next. David Wood will talk about Q number, so the proof that settles that problem. Louis Esperet will talk about non-repetitive coloring. Piotr Micek will talk about p-centered coloring and L vertex ranking. And finally, at the end, Gwen will talk about universal graphs. Thank you for listening, and thank you for attending. Any questions?
Hi, Pat. I had another question, if I could.
Sure.
What other interesting classes do you get when 8 is less? Like when you have 7 or 6 or 2 with anything? Are they classes of planar graphs that we know?
Well, I think, yeah, I don't have an interesting example. Right, so sort of next down is outer planar graphs, but they already have small tree width, so it's kind of pointless to do those. Right, you don't get anything significantly simpler. So I don't have a good example, but that actually opens up another question: is what other classes of graphs might have this product structure? And even more simply, can you find me even a proof for planar graphs that's significantly different from the current proof? And the reason I say that is because all of these other generalizations of this theorem, hiding inside there is an appeal to the theorem for planar graphs. So it would be nice to have another way to get product structure other than appealing to that.
And maybe a related question is, what if you allow tree width 9? So you're going beyond planar graphs, I guess.
Well, so everything that that we say today will be true for those graphs. So they all have constant Q number, they all have constant non-repetitive chromatic number, and so on. If you're asking me what known class of graphs is contained in those things, I don't have a good answer, but it's more general than planar graphs. That's all I can tell you.
Maybe you can say that the 8 in the proof is maybe just an artifact of the proof, and the real value might be 3,
yes,
right?
The 8 in the proof is maybe not optimal. We know that the 3, though, is optimal. So even that you won't get some core graph that has tree width smaller than 3, like we talked about in the second theorem. And David says 7 can be done. So the G is a subgraph of a product of a graph of tree width 7 and a path. All right, thank you everyone for listening. I'm going to stop sharing my screen so that our next speaker can.
So in the meantime, there was another question in the chat, Pat, if you want to
okay,
say something.
Very nice results and talk. Maybe I missed something, sorry if I did. Is there some intuition as why it's the strong product and not some other graph product? I mean, the intuition for me is that the breadth first search tree has edges that are in the tree, and it also has edges that stay within a level. So those would be basically the Cartesian product edges. And then it also has edges that are not in the tree and not staying within a level, so they go between 2 levels. Those are the ones that you end up becoming diagonal edges in the strong product. So without those, you don't get everything. Okay, so our next speaker is a good friend and longtime collaborator of mine, David Wood. David, go ahead.
Thank you, Pat. Good morning to everybody. 6 o'clock in the morning where I am. I want to talk about Q layouts of planar graphs. This is the question that motivated the development of the planar graph product structure theorem that Pat's just told you about. So what is a Q layout of a graph? Excuse me. So for an integer k, a KQ layout of a graph G has got 2 parts. It consists of a vertex ordering, V1 to Vn of the graph, along with a K coloring of the edges. Now, this is not a proper coloring of the edges. The rule is that no two monochromatic edges nest with respect to the vertex ordering. So on this picture here, these two edges are not allowed, right? Because they are monochromatic, they're both red, and one is nested inside the other. So nested means it only refers to disjoint edges. So any two edges that share an endpoint do not nest. Right? So this is the rule that defines a KQ layout. And then we say the Q number of a graph is the minimum K such that G has a KQ layout. You might be familiar with the notion of a book embedding. This is dual to a book embedding. In book embeddings, you would replace the word nest by cross. Here we're interested in the nesting relationship. Let me give some examples that hopefully illustrate this definition. The first is of a tree. Pick your favorite root vertex of your tree and then do a breadth first ordering of the vertices where, so you're ordering by distance from the root, where say the vertices at depth 2, you order them with respect to the ordering of the parents at depth 1. So when you do that, and you think about it for a few seconds, you'll see that no two edges are nested. So in this tangled web of edges in this picture, look, if you stare at it, you'll see there is actually no two nested edges, and that's always the case. It follows immediately from the breadth first property. So trees have Q number 1 because I can simply color all the edges the same color. Let's do a more interesting example. What about a grid graph? Take the graph on the left, the planar grid, and color the horizontal edges blue and the vertical edges red. And now order the vertices row by row by row. Then you see that the blue edges do not nest and the red edges do not nest. So that shows you that the grid graph has got Q number at most 2. But in fact, there's a clever way to do it. You can do it with only one Q. So I should say that the set of edges that have the same color is called a Q. If you order the vertices by the sort of diagonal sweep, as shown in the figure on the left, then in fact no two edges nest. You can see this because between any two of those consecutive gray lines in this picture here, the edges don't cross. And that means when you put those sort of tracks side by side, no two edges nest. So in fact, this grid graph has got Q number 1. So we know trees have Q number 1 and grids have got Q number 1. And this led to an open problem from the very first paper on this topic of Q number. Heath, Layton, and Rosenberg conjectured that planar graphs have bounded Q number. And this was a problem that motivated a lot of research and was considered the major open problem in the field up until a couple of years ago when we solved it. But let me tell you the history of this question. First of all, it was conjectured that planar graphs have bounded Q number. And then Pimaraju, who wrote his PhD on this topic, actually conjectured that planar graphs have unbounded Q number. And Heath and Rosenberg repeated this conjecture. So they basically changed their mind. And Pimaraju actually conjectured that a particular family of planar graphs has unbounded Q number. And it's this beautiful family shown on the right here. Goes by so many different names. Some people call it the stellated triangle, or polytope theorists will call it the stacked polytope. You start with a triangle and put a degree 3 vertex inside the triangle and then repeat that operation. Pick any internal face and add a degree 3 vertex inside that internal face and repeat. And if you go far enough, the conjecture was the Q number will start increasing. But one of the first papers that Vida, Pat, and I wrote on this proved that graphs of bounded tree width have bounded Q number. And this graph family shown on the right here has got tree width 3. So by this theorem, they have bounded Q number, and that disproves the conjecture of Pimaraju. It's not obvious when you stare at this graph family what is the right Q layout. You really need to go through the entire proof for bounded tree width to sort of see what's going on. It's not an intuitive thing, but this family does have bounded tree width, and it turns out that they even have Q number at most 5 by another result that I'll mention later. So what happened for the next 20 years certainly became my personal obsession. I'll openly acknowledge that. This was the mathematical problem I wanted to solve more than any other, and I tried every trick that was known about planar graphs to try and to solve this question of whether planar graphs have bounded Q number. And I worked on it solidly for 20 years, basically. There was an important partial result about halfway through this period. T. Batista, Frati, and Park showed that planar graphs with n vertices have Q number big O of log squared n. Prior to that, the best upper bound was root n. You can get that using Lipton-Tarsham separators, or just with a random ordering, actually, you can get root n. So to get it down to a polylog function was a considerable breakthrough. After this, Vida Domovich found a much simpler proof with big O of log n, as I recall. Anyway, it was still open whether there was any upper bound on the Q number of planar graphs that was independent of the number of vertices. That was what the goal was. And that's what we showed. We showed that planar graphs have Q number at most 49. The constant 49 is not the important thing. The important thing is that there is a constant that upper bounds the Q number of planar graphs. Now you might be thinking, David, why did you spend 20 years working on this problem? Why were you so obsessed by it? And that's a good question to think about. So why was I obsessed by it? Well, the reason I was obsessed was that there were so many methods out there for studying planar graphs, and none of them worked. So I thought, if to solve this question, this conjecture in the affirmative, we're going to have to discover something really new and something interesting about planar graphs that will be of broad interest. So that was my motivation. And the more I worked on this question, what I realized is we needed a global picture of the structure of planar graphs. Most methods for studying planar graphs look at the local structure. Think about the proof of the four-color theorem, for example. It's all about local structure. But this question of Q number was really about the global structure, and that's what made it interesting for me. Now, at one stage in this process, I made a conjecture about the global structure of planar graphs. I said every planar graph is a shallow minor of h times x for some graphs h and x with bounded tree width and bounded degree. I won't explain what shallow minor is. It's not important for this talk, but this conjecture was made because it's the weakest possible conjecture that actually implied planar graphs do have bounded Q number. But the good news is that we proved a theorem that's actually considerably stronger. We replaced this condition of shallow minor by subgraph, which is a much stronger condition. And we replaced x having bounded degree by x being a path. The paths are about the lowest bounded degree graph you could possibly get. So this is what the planar graph product structure says, that every planar graph is a subgraph of h times p for some graph h with tree width at most 8 and some path p. And here's another picture of a strong product. Each row is a copy of h, and for each edge of h and each edge of the path, pick this edge here, say this edge here, then they always produce a K4 in the product. And that's basically the definition of the h times p. So magically floating in this product, you have your given planar graph. Now we developed this theorem while trying to prove that planar graphs have bounded Q number. So what do you need to do to prove that planar graphs have bounded Q number using this product theorem? Well, as I mentioned on the previous slide, we'd already proven that graphs of bounded tree width have bounded Q number. So all that it really remains is to study the products, where you take H times the path. And it turns out that I had already done that a long time ago. I had a paper on Q layouts of products, and this is a consequence of one of the theorems in that paper, is that the Q number of any graph H times a path is at most 3 times the Q number of H plus 1. And let me show you this proof. It's very straightforward. It's really the first thing you would try to do, and it works. So here's the sketch of the proof. So let's imagine that this number here, let's call it K for simplicity. So I've got a graph H, and it's got a KQ layout. So there's a linear ordering of H and a K edge coloring of H, and no two monochromatic edges are nested. So I take my linear ordering of H, here it is.
And I'm a pediatrician in Webster, Texas, independent.
And take my KQ layout of H and pick any edge of H. And this is in one of the Qs, say it's in the ith Q. And then in the product, I'm going to color the edges as shown here. I'm going to have K shades of blue, K shades of yellow, and K shades of brown. And this edge here will get the ith shade of blue, and the yellow edges will get the ith shade of yellow, and the brown edges will get the ith shade of brown. But the red edges, the vertical edges, I'm going to give them all color red. So that's why the upper bound here is 3K plus 1. Right? There's K colors blue, K browns, K yellows, and 1 red. Right? So that's the coloring rule. Here's just another picture with a slightly more complicated graph H. Note that all the edges in H here are non-nested, so they could be all the same color. So up in the product, we do have this actual coloring, and then we do the obvious vertex ordering. We just order the graph, the product, row by row by row, do the obvious thing. And you can check that no two edges of the same color nest. It should be obvious that the blue edges here do not nest because they all come from the same Q and H. Similarly, the brown edges do not nest because they all arise from the same Q and H. That takes a tiny bit of proof, but it's really obvious once you see the construction. And similarly, the yellow edges do not nest. And finally, the red edges do not nest for exactly the same reason as I showed you before in the grid. So that sketches a proof that the Q number of H times P is at most 3 times the Q number of H. There's actually a more general result that says if you take any two graphs H1 and H2, both with bounded Q number, and one with bounded degree, is the degree, then you have an upper bound on the Q number. It's basically the same proof, slightly generalized. So we can now use this to solve the question about planar graphs. Here's our 3 ingredients. Products have small Q number, graphs of bounded tree width have small Q number. And in fact, Weikart had a much better upper bound than the previous one. The previous proof had a doubly exponential function bounding the Q number of tree width. Graphs of given tree width, Weikart got a single exponential with a much simpler proof. But now we just plug all these things in. Take your favorite planar graph G. We know G is a subgraph of H times P for some tree width 8 graph. By the first lemma, we get this is at most 3 times the Q number of H plus 1. H is bounded tree width, so the Q number of H is at most 2 to the 8 minus 1 times 3 plus 1. That's 766, and that's a constant. So that solves the problem of Heath, Layton, and Rosenberg. But we can improve the numbers, and the key is to use this version of the structure theorem where we add the K3 here, and the bonus is that we get that the tree width drops a lot. And because the dependence on the tree width is exponential, this leads to a much better upper bound. There's a similar lemma for the Q number of a product when we add this extra term here. And then there's this nice theorem of Alam et al, and it says exactly what we need. It says if H is planar with tree width H at most 3, then the Q number of H is at most 5. This is exactly applicable to Pemaraju's supposed counterexample. This is exactly the class that he thought had unbounded Q number. But then we can plug all this in exactly the same sort of calculation as before. But now when we apply the Q number of H, instead of having this 2 to the 8 term, we have a 5. And that leads to a much better upper bound of 49. We convinced ourselves that we can get 49 down to 48, but it didn't seem worth writing an extra 2 pages in our paper for the sake of one color. We weren't so focused on the actual number more than just the existence of a constant. So hopefully you can see that this really gives a paradigm for proving that a given monotone graph parameter, say beta, is bounded for planar graphs. Take any monotone parameter beta, then what do you need to do? You need to show that beta on any graph H is bounded by some function f of the tree width of H. And then you also have to show that beta of H times a path is at most some function G of beta of H. And those 2 steps in isolation often are not that hard. And then you just plug it together and you get that for every planar graph, beta of G is at most G of f of 8. And that's, of course, a constant. And just to advertise a new result, this 8 can get reduced to 7. The paper's fully written. I'm just trying to finish it off as we speak. Okay, so hopefully that slide here should be what you learned from this talk. This is what you should be doing, applying it to other graph parameters. Beta, I emphasize that monotone means that it's closed under subgraphs. You need that when you go from G to H times P, because G is a subgraph of H times P. Now, this result generalizes in many ways. Pat mentioned that it generalizes for graphs of given Euler genus. That means it can be embedded on a small genus surface, and it can be orientable or non-orientable. And we get these structure theorems. The first one's for tree width H and most 8. It's very similar to the previous one, but we've got this extra term of K2G plus H. So plus here just means the complete join. So you take your tree width 8 graph, H, and just add 2G vertices that are adjacent to everybody. Now that increases the tree width by 2G, by adding 2G. So this is still a bounded tree width graph times a path. And then there's another version where we get tree width 3, and this is the right structure. It's just one vertex plus H, then times a path, and then times a small clique on the end. But you plug the second result into the machinery and you get this upper bound on the Q number. It's at most 4G plus 49. So it's a small linear term in the genus. Okay, what about minor closed classes? Well, Pat mentioned very briefly that there's a structure theorem for minor closed classes, and this is what it actually says. It says for any minor closed class script G, there are constants K and L, such that every graph in the class has a tree decomposition in which each torso is a subgraph of this nicely behaved graph. H times P, P is a path, H is this tree width K graph, so that's bounded tree width, complete join with a small complete graph KL. So the KL are what's called apex vertices in the Robertson-Seymour graph minor structure theorem. This proof needs the Robertson-Seymour graph minor structure theorem to prove it, or at least that's our current proof. It'd be wonderful to prove this theorem without the Robertson-Seymour machinery. So what does these words mean? Torso means you take a tree decomposition of your graph, and for each bag X, or each node of the tree X, you take the set of vertices at that node and add an edge between any 2 vertices in that bag where those 2 vertices both appear in any neighboring bag. So that's the torso, and as long as your torso, and each torso is very nicely behaved, it has this nice product structure. And then there's an old lemma of Vita Paterni that says if a graph G has a tree decomposition and each torso has bounded Q number, then the original graph has bounded Q number. This actually generalizes the result that graphs of bounded tree width have bounded Q number. And now I just plug these two results together, and you get that every proper minor closed class has bounded Q number. So it was open whether planar graphs have bounded Q number, and now in fact any proper minor closed class has bounded Q number. Now we can apply the recently discovered product structure theorems for non-minor closed classes to get lots of different results. For example, one planar graphs. These are the graphs that can be drawn in the plane with at most one crossing on each edge. They have Q number at most 495. That number is probably not tight. K-planar. Here you have at most K crossings on each edge, and we get an upper bound. Doesn't really matter what that is. It's just some function of K. There's other examples, D-map graphs. D-map graphs are like joules of planar graphs, where instead you say two vertices are adjacent in the map graph if the corresponding faces share a vertex of degree at most D. And the case D equals 3 is exactly planar graphs. But for any D, we get an upper bound, and it's only big O of D squared. And it all comes from having a product structure theorem that's always of the form G is at most H times some path where H is bounded tree width. And sometimes with a small complete graph as the third component. And there's other examples that I won't go into. Let me mention one other application of this. Classical theorem in graph drawing is that every planar graph with n vertices is a straight line grid drawing with n squared area. And Falsner-Lyot of Wismarth asked whether is there a three-dimensional analog of this theorem with better volume bounds? Does every planar graph have a straight line three-dimensional grid drawing with linear volume? So this means the vertices are mapped to points in 3 space with integer coordinates, edges are straight lines, and no crossings at all. Now, it turns out that this question is intimately related to the Q number question, because we proved that every planar graph has a three-dimensional grid drawing where the shape of the bounding box is sort of narrow, and very long. If it's constant by linear, then whether every planar graph has such a grid drawing is if and only if the planar graphs have bounded Q number. And this theorem doesn't really depend on planar here. You can actually write much more general classes here. But now, well, we know that the second condition in the theorem is true. Planar graphs do have bounded Q number. So the conclusion is that every planar graph has a straight line, constant by linear grid drawing for n vertex planar graphs. And it was this question that actually motivated me to first look at planar graphs. So I'm very satisfied to see that this has been solved. Let me finish with some open problems. Well, first, the obvious question is, what is the maximum Q number of a planar graph? It's between 4 and 48. There is a lower bound of 4, which is highly non-trivial. And we have no idea where the truth lies. Another important question is whether the Q number of a graph is bounded by a polynomial function of its tree width. And if you get a better bound for the tree width, then maybe you can get a better bound for planar graphs. But I think a more important question is how broad, what is the largest class of graphs that have bounded Q number? Now, for those familiar with the Nestor-Trilosona de Mendes polynomial expansion scheme and bounded expansion scheme, a really good question is whether graph classes with polynomial expansion have bounded Q number. And we have absolutely no idea, but I think that's a very good question. And it's very much related to the question of what is the structure of classes with polynomial expansion or classes with strongly sublinear separators equivalently. And in particular, can these be described by some sort of product structure? That's a very deep question that would be of widespread importance in graph theory if you came up with any sort of interesting answer. But this sort of question, I find it's too abstract to even think about. That you need to think about really good examples. Like the question of whether planar graphs have bounded Q number was a really good example question to discover the structure of planar graphs. So thinking about examples here is the right approach. And here's a very good example. So do touching graphs of three-dimensional balls have bounded Q number? Now, if you replace 3 by 2 here, it's exactly the planar graphs by Kobe's disk packing theorem. But if you go to 3 dimensions, that's an open problem. The touching graphs of three-dimensional balls have bounded Q number. And if you solve this question, I bet you're going to discover some beautiful structure about touching graphs of three-dimensional balls, which would be useful for lots of problems. And then this would be a key example of classes with polynomial expansion. And then it's probably going to say something more general as well. So these are the sorts of questions I think are important. I like the interplay between theory and examples here. This is this theoretical question, but by looking at good examples, you learn something about the theory. And that's what we've done. We started with the question of whether planar graphs have bounded Q number, and well, along the way, we found the planar graph product structure theorem, which is really the beautiful thing that was waiting to be discovered. So thank you for attention. I'll stop there.
All right, thank you, David. Does anyone have any questions for David?
Yeah, so I'm wondering if K quasi-planar graphs could have a product structure, but it seems to me like that would imply that they have a linear number of edges, which has been an open problem for a long time.
Yeah, that would imply a linear number of edges. H times P has a linear number of edges for sure, for H's bounded tree width. K quasi-planar, so this means that most K pairwise crossing edges. There's much weaker statements that we don't know. There's something called K gap planar, which is in between K planar and K quasi-planar. It says that on every crossing, you can charge it to one of the two edges, and each edge gets charged with K crossings. So that's another nice class, and we don't know whether they have a product structure theorem or a even bounded Q number. Is that right? Yeah, we don't know that. So, but maybe there's some, I'll think a bit more and see if I can think of any counterexamples whether K quasi-planar have product structure theorems. Could be going a bit too far. I can't think of anything off the top of my head, but I'll let you know, Rose.
Thanks.
Anyone else?
I just wanted to ask, is anything known about linear expansion at all, or that's
No.
also open?
That's open. You can replace the question here by a polynomial by linear. And there's even the simplest thing of all is that we don't know whether graphs of bounded layered tree width have bounded Q number. So that's a very specific type of linear expansion.
Okay. Thank you, David. I guess we'll let our next speaker, Louis Esperet, set up.
Sorry, I need 1 minute.
Okay, so here's our next speaker, Louis Esperet, who's going to tell us about non-repetitive coloring of planar and other graphs.
Okay. Thank you very much, Pat. So what I'm going to talk about is joint work with Vida Dujmovic, Gwenaël Joret, Bartosz Walczak, and David Wood. So it's in chronological order, the second like nice, impressive application of this product structure theorem. And yeah, for most of the talk, I'm really going to follow the kind of workflow that David initiated in his talk about the Q number. So somehow, most of the nice properties of the Q number, the fact that it's monotone, that it's easy to compute for graphs of bounded tree widths, that it's easy to compute for strong products with a path, all of this also holds for non-repetitive coloring. So we're going to see that in a minute. So don't hesitate to interrupt me during my talk. Okay, so what is non-repetitive coloring? So the origin of this is in combinatorics on words. When you have a word, so a sequence of letters in some alphabet, the square of a word W is the concatenation of W with itself. So W followed by W. For instance, toe square is toto. And we say that a word is square free or non-repetitive if it contains no square. So for instance, the word cube is square free, but carré, which means a square in French, contains a square, R. And the word repetition also contains a square, it's TI, it's a square, okay? So these two words are not square free. Okay, so once you have this definition, a very natural question is whether you can, given some alphabet, if you can construct large words that are square free. And if you can do that, how many letters do you need in your alphabet to be able to construct large square free words? So that's a very natural question. And of course, you cannot, if you have a single letter in your alphabet, you won't be able to make a square free word on 2 letters. But if you have 2 letters, let's try to construct a large square free word. You start with A, then you have to use B, and then you have to use A again, and then you have to use B, and you have a square. So certainly you need at least 3 letters in your alphabet if you want to build large square free words. And the fundamental result of Thue from 1906, which can be seen as the foundational result in the combinatorics on words, is that you can actually build arbitrary large square free words on the 3-letter and any 3-letter alphabet. So if you have the alphabet ABC, you will be able to construct very large square free words, actually infinite size square free words. And Thue actually gave a constructive way to build this word. You will apply some morphism iteratively. So morphism is that you replace the letter A by a new word and the letter B by a new word and so on. So you start with A and you replace it by ABCAB. And in this word, you replace the small a again by ABCAB, but the B you replace it by ACABCB and the C by ACBCACB. When you do that, you have a new word. And you can repeat this over and over again. And what Thue proves is that if you start with a square free word and apply this morphism, the new word is also square free. So this gives you a way to build arbitrary large square free word. And you can check that every word is a prefix of the next word. So what you do is actually you build an infinite square free word. Okay, so that's kind of solved the question. And now I'm talking about coloring. So what's the connection between this problem in combinatorics on words and coloring? So the notion that we're going to see is the notion of a non-repetitive coloring. And we said that a coloring of the vertices of a graph is non-repetitive if for any pass in the graph, the colors, the sequence of colors on this pass form a square-free word, okay? So you want to forbid all possible paths that would be repetitive. So in particular, for any edge, you don't have the same color on the two endpoints of this edge because this would be a repetition of size 2. And then an edge is just a pass on two vertices. Okay, so a non-repetitive coloring is also a proper coloring. And so the minimum number of colors in a non-repetitive coloring is called pi of G, and it's called the non-repetitive chromatic number of G. And so as I observed, pi is always at least the chromatic number of G. So what can we say about pi? What we just saw, the result that you can find arbitrarily large square-free word. Actually, it's just, I mean, an equivalent way of saying that is just to say that paths have a non-repetitive coloring with 3 colors. So your colors would be A, B, C. And since you can do that for arbitrarily large square-free word, it tells you even that you can color the infinite one-way path with 3 colors in a non-repetitive way. Okay. So yeah, so what's interesting is, as I say, non-repetitive means that you don't have A on some edge, but it also means that you don't have AB on a path on 4 vertices, and not ABC, and so on. So compared to other classical coloring notions, you really forbid an infinite set of patterns, and this is what makes non-repetitive coloring much harder than other classical coloring parameters. Okay, so this was about paths, and if you remember in Pat's talk, he had some kind of sequence of increasingly hard graph classes, but paths were really at the very top. These were the easy graphs, and just after paths we had trees, and for trees you can prove that pi, the non-repetitive chromatic number, is at most 4. So let's see the proof, because it's the only proof that we're going to see in this talk, and it's like it already contains most of the ideas of everything else in the proof. Okay, so how do you prove that trees are non-repetitively colorable with 4 colors? So you take your tree and you root it in some root, and then you order your vertices according to the distance to the root. So you have your layers, okay? And somehow you can view this layering as some kind of projection to some path. So this vertex get projected to this vertex. These 2 vertices get projected to this vertex, and so on. Okay. And then you take a non-repetitive coloring of a path with 3 colors that we know that they exist. And then you assign these colors to the layer. So the first vertex would have color 1, the second layer would have color 2, the third layer would have color 3, the fourth layer would have color 1, and so on. And you try to prove that this is non-repetitive. So you take any path and you try to prove that it doesn't have a repetition. But you have 2 types of paths in trees. So paths that are only going up, Pat called them vertical paths, and clearly every vertical path projects to a path on the right. So if you have any vertical path, it corresponds to a path here, and this path has to be non-repetitive. So it means that every vertical path in the tree is also non-repetitive. But you have another type of path, which is more problematic. It's paths that go up and then down. And these paths, I mean, it doesn't work. I mean, this path here, we have a repetition, 3, 1, 3, 1. So it doesn't work. And what's the reason? Well, the reason is that when we project this path here on the path on the right, what we have is not a path, it's a walk. And we haven't said anything about walks. We just said, let's take a non-repetitive coloring of the path. But this walk, I mean, you don't say anything about this walk. So this is the problem. The main problem, and this will be also the main problem in the remainder of the talk, is that paths on the tree, when you project them, they become walks. Okay, so you need something about walks. And one way to fix that is to say, okay, the main problem here is that we have somehow 1, 3, 1, or 3, 1, 3, 1, and we have a 1, 3, 1. And so if you say that instead of forbidding all repetitions, your coloring of the path here on the right also forbids all palindromes. So palindrome is a word that you can read either from left to right and right to left, and it would give the same word, like Laval, for instance, L-A-V-A-L. If you forbid repetitions and palindromes here, you don't have this problem. Here we, like this 3, 1, 3, it's a palindrome. If you forbid that, you won't have this situation. So how do you get a coloring with no repetitions and no palindromes? Well, you just have to take the sequence of 2 and add a 4th letter every now and then. And now you can check that you don't have any repetitions, and also you don't have any palindromes. So if you replace your coloring with 3 colors by this coloring with 4 colors now, and you project it in your tree, now you can check that you don't have any square. Because if you had a square, it would mean that you either have a repetition here or a palindrome. Okay, so you can color trees with 4 colors, and really the most important thing is that paths, when you project them, they're not necessarily paths, they are walks. So you have to be careful. Okay, so trees, you can color them with 4 colors, and the very natural question is, once you know how to do things with paths and trees, is what about planar graphs? Planar graphs, we know that they have a chromatic number at most 4. What about the non-repetitive chromatic number? It was conjectured that, or it was asked whether, so Alan, Grichuk, Aluchak, and Radan asked whether planar graphs have bounded non-repetitive chromatic number. And we are going to use the product structure theorem to prove that this is indeed the case. Okay. Any questions so far? Okay. Right. So remember.
How often do you insert the 4th color? Is it every 3rd vertex?
Yeah. Exactly.
Yeah. Okay.
Yeah, and you can check that you don't have any palindrome, because otherwise you would have a repetition. So you're raising the fact that it has no repetition. Thanks. So yeah, so what do we know about this problem? We are going to need results about tree widths. So fortunately, it was proved by Küngen and Pelsmeyer that if the tree width is k, then pi is at most exponential in k, 4 to the k. So we're going to need that. An interesting other result is that for graphs of bounded degree, pi is also bounded. And prior to our work on this problem, the best known bound for planar graphs was log n. So it was quite small, but increasing with n. And now we're going to use the product structure theorem that, let me restate it. So the product structure theorem tells you that any planar graph you can find as a subgraph as some kind of grid of some, like this grid here on the right, where columns are paths and rows are the same bounded tree width graph. So rows are almost like trees, almost the same trees. Okay, so this is the result that we're going to use, and exactly as David said, okay, the only thing we need to prove, if you a subgraph H of G has non-repetitive chromatic number, at most the non-repetitive chromatic number of G. So it's monotone, but I'm not taking subgraphs. So if you want to use this theorem, the only thing we need to prove is that whenever you take the strong product of a graph of bounded tree widths and a path, the non-repetitive chromatic number is bounded. Right? This is the only thing that we need to prove, because non-repetitive chromatic number is monotone. Okay, it's not always the case, and you have to be careful, but this is a very important property for using this kind of theorem. Okay. Okay, so let's try to see how we could prove that. Take a graph with bounded tree widths and a pass, and the product has bounded non-repetitive chromatic number. And we know that graphs of bounded tree widths, they have bounded non-repetitive chromatic number. So let's say take any graph of bounded non-repetitive chromatic number, take the product with a pass, and this has bounded non-repetitive chromatic number. How do you prove that? Well, you can do exactly as before, as the proof in the case of the tree. So you would take a coloring of this pass with 4 colors, no repetitions, no palindromes. Take a coloring of this graph with a bounded number of colors, and define a new coloring as the Cartesian product of the 2 colorings. And you cross your fingers and you want to show that this has bounded non-repetitive chromatic. This is a non-repetitive coloring. So again, you take a pass in your graph and you say, I want to show that this is non-repetitive. And then what you do is you project your pass vertically and you project your pass horizontally, and you try to understand what happens. But the problem now, like remember for trees, when we project a pass, it can be a walk. So this is problematic. But here in this case, it's even worse. It's not even necessarily a walk. If you project this pass here vertically on this pass, it's not even a walk. You stay at the same place. It's called a lazy walk for people who do probability. It's a walk, but sometimes you're a bit lazy or you're a bit tired and you stop at a vertex for some time. So it's not about walks, it's about lazy walks. And if you want to really prove this problem, you now realize that you don't want to prove something about repetitive paths. You want to prove something about repetitive walks or even lazy walks. So this is so we can't really actually prove that if you take a graph with bounded non-repetitive chromatic number and take the product with a pass, it has bounded non-repetitive chromatic number. We don't know how to prove that. But if we modify the definition a little bit, and by defining some parameter, which is about non-repetitive lazy walks instead of pass, then we can actually prove that what we want. Like take the product of a graph with bounded pi star with p, then the new pi star is bounded. Okay, but we can also prove that this pi star, which is a bit stronger, is also bounded for graphs of bounded tree widths. And it's actually exactly the same proof as that of Kungen and Pelsmayer. And if you like, this parameter pi star is kind of implicit already in their proof. So we have these two things, and it's over. Every planar graph is a subgraph of h times p. So pi star of g is at most pi star of h times p, which is at most 4 times pi star of h by the first result, which is at most 4 times 4 to the 8. It's at most 4 to the 9. It's bounded. So as David said, we can use a different structure theorem and get something a bit better than that, maybe 768. But and you can push things, but not so much further for the moment. Even getting under 50 seems out of reach for the moment, but it's bounded. Okay, so this is the result. Planar graphs have bounded non-repetitive chromatic number. But this is not the end of the story. And using the product structure theorem, you can go a bit further than that. So again, David mentioned that. So the structure theorem holds for graphs embeddable on a fixed surface. And you can even add a bounded number of so-called vortices, which are, you can think of them as being small interval graphs that are pasted in some faces. But again, this is where the product structure theorem stops. Once you are further than that, I mean, like more somehow less simple than that, you have to stop using the product structure theorem, and you have to use other tools. Now the remark is that if you add a single vertex to a graph of bounded non-repetitive chromatic number, a vertex with any neighborhood, then you only increase pi by a constant, by a constant of 1. You add one vertex, you just add 1 to pi, because you can just take a new color for this vertex. So if you add a constant number of vertices with an arbitrary neighborhood, you only increase pi by a constant. So these two things put together they tell you that if you take any graph embedded on a fixed surface with a bounded number of vertices and apices, it still has bounded non-repetitive chromatic number. And then we can use the graph minor structure theorem of Robertson and Simo. As David mentioned, you can it says that graphs from any proper minor closed class, they're obtained from these graphs embeddable on a fixed surface plus a bounded number of vertices and apices. These are the building bricks. And you take, the graphs in any proper minor closed class, they're obtained from these bricks by repeatedly doing click sums. So you take 2 clicks on these 2 graphs and you glue these clicks. Okay, you do that repeatedly. And using this theorem, we can extend the results to any proper minor closed class. So for any proper minor closed class, the non-repetitive chromatic number is bounded. Okay, but again, we need to go further than the product structure theorem to get that. We don't have this for free from the product structure theorem. But this is again not the end of the story. As we saw, graphs of bounded degree, they have bounded pi. And we can again use this and another nice structure theorem, this time for graphs that avoid a fixed topological minor. So you avoid all subdivision of some graphs. Then again, the structure theorem tells you that you can, you can describe this class by taking click sums of simpler graphs. And the simpler graphs are either graphs embeddable on a fixed surface with bounded number of vertices and apices, or graphs of bounded degree. But these two have a bounded non-repetitive chromatic number. So again, we get that graphs avoiding a fixed topological minor, they have bounded non-repetitive chromatic number. And this is a bit crazy because 2 years ago, we didn't know whether planar graphs had bounded non-repetitive chromatic number. And now we have it for all proper minor closed class or classes that are closed under taking topological minor. This is much broader in some sense. So this is very surprising that we get all this at once. But again, the important thing is that with the product structure theorem, you can go quite far, but not all the way to the end. You need to stop at some point and you have to use other properties of your parameter, that you don't increase your parameter too much when you add vertices, and that it's bounded for graphs of bounded degree, for instance. You need to have all these nice properties. The product structure theorem cannot do everything for you. You have to work at some point a little bit if you want to go further than planar graphs. Okay, so thank you. I'm done.
Thank you very much, Louis. Does anybody have any questions for Louis?
Yeah, what about a list version of non-repetitive? Does that make sense? And are there results for that?
Yeah, it totally makes sense. And right now, the typical application of this result do not say anything about lists. But the problem is with lists is that, as far as I know, even for trees, this is unbounded. So for pass, it's at most 4, and it's kind of conjecture that it's at most 3. The right answer should be at most 3. But once you go for trees, it's not bounded anymore if you have lists.
I see.
So there's no hope to prove something similar for lists in planar graphs.
Okay, thanks.
I hope I'm not saying anything. So the specialists do not hesitate to tell if this is wrong, but I think it's unbounded for trees.
Yeah, so David says that you need some bounded degree assumption for list coloring.
Yeah, but for bounded degree, you have it for all graphs of bounded degree, not just planar graphs of bounded degree. Yeah, exactly.
You have it for all graphs of bounded degree, even for lists, you're saying?
Yeah, because the proof for bounded degree works with list in a very easy way. Like it's the Lovász local lemma. Whether you have lists or not, it doesn't change.
I see. Sure.
Yeah, so already you have bounded. Yeah, exactly. Any more questions? Yeah.
Yeah, just a quick question. Nice talk. So you mentioned that the square free result on words is really about the non-repetitive chromatic number of the one-way infinite path. So it seems as if it would be nice to have some results for infinite graphs. Have you thought about that at all, or?
No, it's a good question. So yeah. So so you can use the result for the infinite path using the appropriate structure theorems. For, I would say, I think you have something for infinite planar graphs. So like if you look at the product of an infinite path with anything of bounded pi star, it would have bounded pi star in the same way, right? So because you can always take the product with this infinite path and you do the trick where you avoid palindromes and repetitions. So any infinite graph that you like, any product of a finite graph, but if it's finite, it should be okay. Yeah, for instance, any product of a finite graph with an infinite path should be okay. For instance, I would say, because you can do the same proof basically. I would guess so. Yeah. And now the question is, yeah.
Isn't the non-repetitive chromatic number of any infinite graph equal to the maximum non-repetitive chromatic number of the finite subgraphs? Just by
by compactness.
Compactness. Koenig's lemma works, right?
Yeah, but now you have an infinite number of forbidden patterns. I don't think. Do you think? Are you sure? Okay. I need to. I would need to check. But if in this case,
David, I think you're right.
Yeah. Okay. So in this case, yeah. So then you have for free the result for two-way infinite path if you want, but it's not as constructive as actually giving it in some sense. It's a compactness argument. It's just it's a bit cheating. If you want.
Thanks.
But if you want a constructive way, you of anything with the path, you can really build it using the coloring of the path and taking the product. Yeah. Okay, thanks for the question.
Okay, thank you very much, Louis. That was very nice.
Yeah, I don't know how to make a two-way infinite path in an explicit way, but maybe that's easy. I don't know.
All right, so let's let our next speaker, Piotr, set up. Thank you again.
Okay, let's see how smooth it goes. It does look quite smooth. Slideshow. So shall I just start?
Our next speaker is Piotr Micek, who is going to talk to us about two kinds of graph colorings.
Yes, hello everyone. So the purpose of this talk is to show a quick application of the product structure theorem. We will just focus on planar graphs, so we're not going to go higher, although as you've seen, we are able to do so. And we will see two recent results, substantially improving the state of art with a very simple, straightforward outline of the proof. The outline you actually have seen. So yes, let's look at the coloring we are going to study for most part of the talk. So how about we color the vertices of a graph in such a way that for every connected subgraph, we have a color that is used exactly once. That's a fancy coloring. So let's see, we have a graph. Yeah, this is like a big thing. And then for every connected, obviously non-empty subgraph of it, we require in our coloring that there is a color that is used exactly once here in this yellow area. And then the coloring is okay. And this has a name. It's a centered coloring, and the centered chromatic number of a graph is the minimum number of colors you need in such a coloring. And yes, maybe first thing to say is that this is a centered coloring is actually proper coloring, because edge induces a connected subgraph, and if you have the condition says that you cannot have the same color on both ends, right? So it is proper. So chi is less or equal than the centered chromatic number. But in fact, this peculiar parameter coincides with something which is quite studied with the tree depth of a graph. So what is quickly the tree depth? The tree depth is a minimum height of a rooted forest, such that you can find your graph is a subgraph of the closure of that forest. And now, if you think of a graph as a 3x3 grid, then if you think of the forest as this tree, rooted forest, so the root is here at the bottom, yeah, then when you close this forest, the closure of this forest is a graph that you obtain from the forest by adding an edge between any two vertices that are in the ancestor-descendant relation. Yeah, that's the closure. And then you can see here that in fact this grid, our graph is a subgraph of the closure of our initial forest. And that means that the tree depth of our initial graph is at most 5. 5 because this is the height of the forest. Height is the maximum number of vertices on the root to leaf path in the forest. So that's the tree depth. Tree depth is a parameter. It usually is compared with the pathway of the tree width of a graph. Heavily studied structural graph theory, also algorithmic applications. And indeed, it coincides with the centered chromatic number. This is easy in both directions. So let's have a quick look. For example, if we have this representation, this witness for the tree depth, we can color the vertices of a graph layer by layer using one color per each layer. And then I claim that this is actually centered coloring of the initial graph. Why is it so? Well, because whenever you take a connected subgraph, you should convince yourself that there is a vertex that is below all the other vertices in your subgraph. Yeah, like a minimum. This comes simply from the fact that no edge goes like it's like a DFS. All the edges are kind of vertical, no edge between two disjoint branches. So this proves one of the two inequalities. The other is also easy. So it's the same thing, but maybe a bit fancier. And here's an idea how to interpolate between the two parameters, between chi and the tree depth. So fix your integer p, +1, and then a vertex coloring is called p-centered if now for every connected subgraph, either this subgraph carries lots of colors, more than p colors, or again we have a color that is used exactly once. So this color used exactly once would be a center. This vertex carrying this color would be a center of the subgraph. So now we don't require that every connected subgraph has a center. We are satisfied if it's hit by a lot of colors. Then it's still centered, p-centered. Yes, so that's a definition. And then we have a p-centered chromatic number. And it should be quite obvious that we have a family of parameters that is increasing when p grows. And the first chi, yes, so one-centered coloring is nothing else but the proper coloring. If you look at the definition, and the two-centered coloring is known in the literature as a star coloring of a graph. While if you replace p with the infinity, you actually coincide with the first definition I gave you, which is just the centered coloring. So yes, indeed, we are going from chi to the tree depth. So okay, we have a family of parameters, and this family is actually known, and the reason it's interesting, one of the reasons I guess, is that it captures important concepts in sparsity. Sparsity is a relatively new research line in structural graph theory, introduced mainly by Jarek Neshitky and Patricio Sonado-Mendes. And there we have concepts of bounded expansion and lower denseness for classes of graphs. And we can capture these concepts using this family of parameters. So for example, a class of graphs has bounded expansion. I'm not going to tell you what is it here, but it is exactly the same. We could define it as there is a function such that for every integer p and for every graph in the class, the p-centered chromatic number of a graph is bounded by a function of p only. Okay, so so that's the family of parameters, p-centered chromatic numbers, and then what we know is okay, we have bounded expansion, and we actually know that all the nice families of graphs from structural graph theory actually have bounded expansion. All that comes to our mind. So planar graphs. I said I will talk only about planar graphs here. Bounded degree graphs as well, and you can go higher and higher. So so there are bounds. Yeah, there are bounds for p-centered chromatic numbers when for planar graphs. So what are the bounds? And when we look at the general statements, yeah, going from the bounded expansion, first results on p-centered colorings, chromatic numbers, then these bounds are large. I'm actually not sure how large they are, but quite large. And it was for a moment an open question if we can get a polynomial bound for planar graphs, and we can. And this is actually the main result. Well, at least in the narration, the main result in the narrative, the main result of Michał Pilipczyk and Sebastian Sieber's paper, which was referred to here in this session. So they prove that the p-centered chromatic number is polynomial for planar graphs. It's big O p to the 19. And well, using the product structure, we can get a quick proof with the bound well p cubed log p, given that we know the bound for the trie-width or simple trie-width situation. So let's have a look at the outline of this proof. Yes, so this we are going to need as a tool. Results for so for the bounded trie-width, the results were known in the very same paper. Michał and Sebastian proved that chi p is at most p plus k choose k when the graph has trie-width at most k. And believe it or not, this bound is tight, absolutely tight. I like it. It's not usual, right? And here it will get a better bound if we use the bound for simple trie-width. So we didn't actually define during today the simple trie-width, but we will use it only for valued 3, and simple trie-width 3 only means that the graph has trie-width at most 3 and it's planar. So so then the bound you see the asymptotics. Yes, and here is the hero of the series of talks, the product structure theorem, and actually we're going to use this this version to get a good exponent in the polynomial. And yes, and now we're entering to the proof situation. So similarly, I guess to the situation in Louis talk, we need to have a kind of strengthening of the coloring of the property, and this part of the proof will be here, where we study an auxiliary coloring. Let's call it a distance L coloring. So L again is an integer, positive integer, and the vertex coloring is distance L coloring. If just for any two vertices in the graph, if they are in distance less or equal L, they have different colors. That's it. And then we'll denote this way the respective chromatic number, minimum number of colors in such a coloring. And from the definition, you can see that under this coloring, if you have a path connecting two distinct vertices of the same color, then this path must contain more than L colors, where L is this parameter that we are playing with. So just from that, we can see that the distance p coloring is actually a p-centered coloring. So this is like a strengthening, a big strengthening of our initial coloring. But it will become useful in this moment that we want to lift the bound through the strong product. We will see this in a moment. So here is a kind of preparatory observation that if we just take two of the graphs that we see in the product, so the path and the K3, then we can simply color it in this distance p fashion using just 3 times p plus 1 colors. And this is just a very obvious coloring. You just enumerate the consecutive triangles. Yeah, this is the graph actually, p cross k3, right? And we enumerate the corresponding triangles like modulo p plus 1 with integers modulo p plus 1, 1, 2, 3, p plus 1, and then again 1, 2, 3. And within each like a number, we are actually use 3 shades of colors. And that's the coloring. So we are actually using this number 3 times p plus 1 colors. And this is a distance p coloring because if we are using the same color, this is with the triangles that have the same identifier modulo p plus 1, and they are far away. They are more than p far away in the graph. So that coloring works. And here is the critical technical inequality. Yes, so when we now take 2 graphs and we take a strong product of those, yeah, and we are interested in the p-centered chromatic number of the resulting graph, then we can bound it just taking the p-centered chromatic number of one of those, say the first one, and multiply it not by the p-centered chromatic number, but by this stronger chromatic number, the distance p chromatic number, and this will work. And but first, this is all we need to complete this outline that you have seen already a number of times, because, well, a planar graphs admit product structures. Yes, so G, when it's planar, it is a subgraph of H cross P cross K3, where H has a simple trivet at most 3. And now we take a p-centered chromatic number of G, and we want to bound it. So first inequality, yes, it comes from the product structure, and it also comes from the fact that our parameter again is monotone. Yes, so okay, it's enough to bound this number. And now by this lemma, we can factor out the product. Yeah, so we take just the p-centered chromatic number of H, and we multiply it by the stronger chromatic number of P cross K3. But this is a simple graph. We have seen it. This is a number. We can put it here. And now it's all about the p-centered chromatic number of a graph that has bounded trivet, simple trivet. Yes, so we can put the bound that we know. In the simple trivet situation, if this is 3, then this is 1 less, and it's p squared log p. So this gives us the p cube log p bound. And all we need to see is the argument for the lemma. Okay, so let's go for it. So that's the statement. That's the inequality we want to prove. And the proof is really straightforward in nature. So if you want to color a product and you're bounding by the 2 chromatic numbers, you should take the product coloring. Yes, so just do it. So take a p-centered coloring of H1. Yeah, let's call it C1. Take a distance p coloring of H2. Let's call it C2. And now consider the product coloring. And the claim is that this product coloring is a p-centered coloring of the full product. Well, how to prove it? If we want to prove that something is a p-centered coloring, we should consider a connected subgraph of our initial graph. Our initial graph is a product, so we consider a subgraph G of H1 cross H2. It's connected. And now we want to show that under phi we have a vertex with a color that is unique there, or lots of colors are used there, more than p colors. This is our goal. So okay, we have this G. We consider projection of G on the so G is you know, the vertices of G are pairs of vertices, right? So we can project them on the first coordinate, on the second coordinate. And these are subgraphs of respectively H1 and H2. And from the nature of a strong product, if the G was connected, the subgraphs are also connected. The projections are connected, yes? This comes from the fact that when you have a path in the product, this projects to the lazy walk, Louis called it in the projection. Yes, so we have two projections, and now let's look at the first projection, the one where we have a p-centered coloring, so the weaker coloring. And here we have an alternative, either because we have a connected subgraph, G1 is connected there, G1 is connected in H1. So either C1 uses lots of colors, and if this is so, we are absolutely happy, because if we have lots of colors on the projection, then we have lots of colors in the coloring, the actual coloring. So we have to look at the other option where C1 there is a vertex, there is a color, C1 color that is used exactly once in G1, and here we have to work with it. So take such a vertex D1 in G1, and we were in the projection, so there is a vertex in the graph we consider G. That on the first coordinate has B1, right? So now there are two options. One is trivial for us. So either this vertex D1W in G has a unique color under our product coloring in the graph G, and this absolutely makes us happy because we are looking for such a color. This is as desired, or not. And if not, then there is a second vertex distinct from our one, yes, that carries the same color in our product coloring. Okay, so but our graph G that we have taken is connected. So we have a path in G connecting the two vertices. And so this is Q, this is a path in G. The G is a subgraph, I remind you, of the strong product. And now we can look at this path and we project this path on the second coordinate. And when we project the path on the second coordinate, as I said, we have a walk or lazy walk, right? And this walk connects two distinct vertices, W and W prime are distinct, of the same color under C2. And that's a situation perfect for this strong distance P coloring, because we have two vertices of distinct coloring, of the same color that are distinct. So they have to, any path between them, and the lazy walk contains a path between them, must carry lots of colors. So we have lots of colors, more than P colors there. So we carry more than P colors in the actual product coloring, and this completes the proof. And this completes the actual statement of the bounds for the p-centered chromatic number. Yes. Yes, that's one time this outline. Now let's have a look at the second, quite similar coloring, vertex ranking. So a vertex coloring of a graph, I call a vertex ranking now, if for every connected subgraph of my graph, there is exactly one vertex that carries the maximum color. Yes, so in the definition, this is very close to the centered coloring. In the centered coloring, we required a color that appears exactly once. Here we require that the maximum, okay, first of all, we are coloring with the integers, yes. And second, we actually require that this color that has the largest value appears exactly once. So this might be a stronger property. And then, okay, the vertex ranking number is the minimum number of colors we need to color a graph in this way to have a vertex ranking. And the thing is that this actually coincides with tree depth again. Although so one of the inequalities is trivial, but the fact that we require that the maximum value is unique doesn't increase the parameter. This has an easy proof again. We're not going to do it, but it's yet another way to look at the tree depth concept of a graph. And here is again a proposition how to interpolate and how to introduce a family of parameters here, quite different from the p-centered ones. Let's have a look. So we have an integer p, And we have a vertex coloring, which now we are going to call a P ranking. So it's a P ranking if for every subgraph, and now the subgraph should be connected still, but I don't write it here because I require that it actually has a bounded diameter at most P. So every subgraph of diameter at most P of my graph has the property under this coloring that the maximum value of a color appears exactly once. Yes, so you see that we are actually we are playing with the definition of the vertex ranking. So we don't require the maximum value to be the center all the time. We just want it for all connected subgraphs. We just want it for connected subgraphs of small diameter. And this diameter P is the thing that grows when we grow the parameter P, yes? So in infinity, obviously, this will be just the vertex ranking and the vertex ranking number. So this parameter VRP is the number, so the P ranking chromatic number, right, is the minimum number of colors in a P ranking of our graph, yes? And here is the visualization, yes, you have a graph for every connected subgraph of diameter at most P. There is this vertex that carries the maximum color, and this maximum color appears only there. So again, we have this chain of inequalities, and on one side we coincide with the 3def, and on the other side we coincide with the chromatic number. But here, so that here the situation is quite different, and well, it is well. You see the bounds. The n is the size of the graph, the number of vertices, and here we have already for trees. The second vertex ranking chromatic number grows with n. Yes, this is very different situation. And yeah, so the first vertex ranking is just the chromatic number, so it shouldn't grow with trees, right? But the second does grow, and there is a quite easy argument that if you look at the P vertex ranking number for planar graphs, then you can bound it by log n times P. And so we could open here a discussion: what is the right asymptotics for the P vertex, for the P ranking chromatic number of planar graphs? It is quite a small gap, right? Because it's between log n over log n and log n. And the trick is that the actual truth is neither of those, yeah. And it is known. So for every P greater or equal than 2, right, not 1, then the actual asymptotics is log n over log n, and this is tight. This is a result of Boze, Dymowicz, Jawar, Sinech, and Pat, who is here. And again, it's a quick application of the product structure theorem, and actually it's the very same application, it's the very same outline. So in order to succeed with it, you need the result for simple triwit, yes, and they did provide it. So when simple triwit is most k, they provide the bound, which is log n over, and here we have k times the iterated log in the denominator. So we will apply it for k equals 3. So that's why we have 3 logs, like here in this bound for planar graphs. And actually, from the fact that this is tight, we have already a lower bound for planar graphs, yeah, because simple triwit at most 3 is actually planar graphs of 3 at most 3. So this statement already contains a lower bound of this main statement here. And for the upper bound, we just go through the product structure, the very same we did a moment ago. So this P vertex ranking of the product is bounded by the multiplication of these two numbers. Again, distance P coloring on one projection, and the actual parameter that we look at in the other projection. And the proof is very much the same of this inequality. And the same is the outline of the proof. Here, when the simple triwit situation comes in, we plug in the bound, and since the bound is large, yeah, it grows with n, so the bounds for planar graphs grow with n. Yes, so that's the two quick applications. In fact, one and two with 2 facets. Thank you for your attention.
Thank you, Piotr. And does anyone have any questions?
I have a question. on the last result you're mentioning, this result is for planar graphs. Do the trees get up that high, or is there a better upper bound for the trees?
No, trees, I mean, Pat, you can correct me, but let me make a statement that this asymptotics actually comes from the bounded symbol tree width situation. Yes, so if you're looking for this exact asymptotics log n over log n, I bet you have to look at the stack triangulations. And
you need triangulation.
Yes.
Yeah.
So I mean the lower bound you state there for trees, is there a matching upper bound?
So there's even a stronger upper bound. So outer planar graphs have a log n over log n upper bound. And that's because they have simple tree width too.
Right. Okay.
Yeah.
Yeah.
Okay, thanks.
Thanks, Pat.
Hello, Piotr. David here. Is the distance p chromatic number of H2 a lower bound on the p-centered chromatic number of H1 times H2?
Why it should be?
I don't know. I'm asking, do you have to use this distance p coloring in the product?
Yes. Okay, then I didn't get your question, but you cannot replace in this inequality the stronger distance p chromatic number with the actual p-centered chromatic number. Then this is simply not true. And the moment in the proof that you actually need it is at the very end, where you.
I understand you need it in the proof, but is it really essential?
I convinced myself, I think, that there is a simple example. It doesn't, I will think about it for the rest of the session. Maybe I'll write you, but I don't remember it now.
Oh, well, I guess a star times a star would be would provide a lower bound. Would it? Anyway.
I will tell you in a moment.
Okay.
So thank you again, Piotr. Thanks especially for presenting a result of mine. It's always scary trying to talk about someone else's results.
Especially if the person is in the room.
Yes. And our final speaker of the session is Gwenaël Joret, who will put up his slides. And I guess before he does, or while he does that, I'd also like to thank the audience who is hanging on valiantly throughout this session, which must be late at night for people in Europe. It's already dinner time for many people in North America. So thanks for sticking with us. Go ahead, Gwen, when you're ready.
Okay. Thanks, Pat. Okay, so hi everyone. I'm going to talk about some joint work done with Vida Dujmovic, Louis Esperet, Cyril Gavoil, Piotr Micek, and Pat. And it's about universal graphs for planar graphs. So let me dive right into the topic. So if you have some set of graphs that you care about, some set F, a universal graph is a single graph that contains every member of your set as a subgraph. So typically in this context, what we do is that we take some class of graphs that we care about, for instance, planar graphs or trees or cubic graphs, and then we fix the number of vertices. So we look at n vertex graphs in such a class, for instance, n vertex planar graphs. And we want to find a universal graph for these n-vertex graphs in your class. So for instance, for the n-vertex planar graphs, which is good in some sense for some measure of good. So of course, since we want to realize our graphs as subgraphs, we could always take a complete graph on n vertices. That's always universal. but you would agree that that's not a very interesting universal graph. And typically what we want to minimize here is minimizing the number of edges in our universal graph, right? So we would like to do at least better than the quadratic bound in N. So that's the main question I'm going to address in this talk. What is the minimum number of edges in a graph which is universal for n vertex planar graphs? And before we continue, let me emphasize that the universal graph does not have to belong to the class we look at, right? So if I look at universal graphs for planar graphs, the universal graph does not have to be planar. And typically it won't be. Okay, so that's the definition we are going to play with. Now let's look at some tools. A key tool in this context is that of separators. In this talk, for me, a separator will be a subset of vertices, so that when you remove it, you can group the components into two sets, each of which have size at most 2/3 n, right? So it's the 1/3, 2/3 definition of separators. Like on this picture, I remove X, and then I have two sides of size at most 2/3 n. And what I suggest we do before we really address planar graphs is to look at trees. It's a good warm-up. And some of the ideas that we are going to use for trees, which is actually a simple case, we are going to meet them again in more elaborate versions later in the talk, right? So it's a good way to start. So let's say that we want to build a good universal graph for n vertex trees. And again, this means not too many edges. So what do we know about separators in trees? Well, we know that there is always a vertex, which is a separator. That's very easy to prove, and one of the most useful facts about trees. So if one would think how to build a universal graph for trees, it's likely that the first thing we would try would be the following. Okay, let's take this vertex, which is a separator of your tree. Let's call it V, and we embed it here on this vertex V. And now we are going to make that vertex connected to everything else in the construction of our universal graph. So we are going to make that vertex universal. And since it's a separator, left and right, after we remove it, has at most 2/3 n vertices. Left and right, it's a bunch of components. So left and right are forests. So they are contained in trees. So left is contained in a tree and at most 2/3 n vertices. Right is contained in a tree and at most 2/3 n vertices. Right, so we can just recurse and put a construction for 2/3 n on each side. And then we could actually observe that, well, one of the two sides will have at most half of the vertices, right? So on one side, you can put at most n/2, right? So you can put the construction for 2/3 n on one side and the construction for n/2 on the other side. And that would be a definition of a universal graph. So hopefully you're convinced that this is a valid construction of a universal graph. If not, feel free to interrupt me at any time during the talk, of course. So what about the number of edges? Well, I'm not going to do the analysis, but if you do the counting, you will get that the number of edges is something like n to the 1.3. So it's already much better than quadratic. It's not a near linear bound though. And intuitively, what is going wrong in this naive construction is that we are not splitting the set of vertices in half exactly at each step, right? So we have a side where we spend 2/3 n instead of n/2. And we would like really to split our domain in half. That's the intuition. So the next thing to try naturally is to use better separators, separators that I call perfectly balanced, meaning that when you remove such a separator, a perfectly balanced separator, there is a way to group the components into two sides, each of which not only has size at most n/2, but even more stronger than that, both sides have exactly the same size, right? So it's n minus the size of the separator of the two. And it's no longer true that in a tree you can always find a vertex which is a perfectly balanced separator. That would be too good. But it's an easy exercise to see that you can always find log n vertices or big O of log n vertices. that form a perfectly balanced separator in a tree. Now, many ways of proving that. I'm not going to do it here. But that's a very natural thing to use if you want to build a universal graphs. And that's like a basic brick in all these constructions of universal graphs. So let's do it for trees. So what's the updated construction for trees? Well, we are ripping off this perfectly balanced separator on log n vertices. We make it a click, complete graph, and we make it universal to the rest of the construction. So we link all these vertices to everything else. And then we recurse on each side. But now on each side, we know exactly how many vertices we are going to have. It's n minus the size of this thing over 2. And then we put a construction for this number of vertices on each side. And notice that here, actually, this construction is really efficient in terms of number of vertices, because this universal graph has exactly n vertices. There is no blow up in the number of vertices. So it's a universal graph on n vertices for trees. Hopefully you're convinced that this works for trees. And now let's look at how many edges do we spend when we do that. Here, the analysis is really simple, because let's look at what happens in one step. See, at the first step, the number of edges we put down is roughly log n times n, so it's n log n. And the recursion depth will be log n. So there will be an upper bound of n log squared n on the number of edges in our construction. So it's a near linear bound, and it's almost the correct answer. So it turns out that you can shave off sorry, an extra log n factor, and that was proved by Chung and Graham in 1983. So the best possible bound is n log n. So their construction is a bit more involved, but it uses some of these ideas, but with extra tricks as well. Right, so n log n is the right answer, and log squared n is really easy using this construction. For the rest of the talk, I'm not going to care too much about extra log factors, so this will be good enough for what we are going to do. Okay, so hopefully this gives you at least now some idea of the tricks you can use to build universal graphs, and you probably noticed that it's not really there is nothing really special about trees here. What we really use is the existence of separators, right? So if you have a class of graphs, say closed under subgraphs, that have small separators, say of size at most s, where s could be a function of n, then you can do exactly the same strategy and you will get some universal graph for the n-vertex graphs in your class. So imagine that you have some fixed class of graphs, like planar graphs, and you have small separators. Then if you have small separators, then you have small perfectly balanced separators. You just pay an extra log n factor. This is an easy exercise that I'm not going to do. And then you can do the exact same construction, and then you get this number of edges, at least as an upper bound in your universal graph. Size of the separator times n log squared n, right? So for trees, the size of the separators was 1. But if you end up playing with classes of graphs with small separators, but not quite as small as like constant size, like say you have n to the alpha for some alpha strictly less than 1, like root n for planar graphs, for instance, it turns out that in that case, the log n factors disappear because there is a geometric series phenomenon, right? So you actually have perfectly balanced separators of size big O on the size of the separator, and same when you do this construction, the extra log n factor again disappears, simply because, well, at each step it decreases, right? So if you have root n, then it's root n over 2, root n over 4, etc., etc. So the log n factor actually gets amortized. Anyways, what is the bottom line of this remark? The bottom line is that, say, if you look at planar graphs, you have root n separators. So you have root n perfectly balanced separators. You do this construction, you're using root n times n edges in your construction, using still the same construction. So that's n to the 3/2. And that was the best known bound proved by Babai, Chung, Erdős, Graham, and Spencer in 1982. So that's essentially what they did in that paper. They proved that for planar graphs, you can use root and separators, and actually for any subgraph classed with root and separators, you get universal graphs with that many edges. And well, until recently, that was the best known bound, right? So the question was, can you go below n to the 3/2? Can you get a near linear bound? And so that's what we did together with Louis Esperet and Pat Morin, but it builds heavily on an earlier paper of us with this superset of authors here that I'm going to talk about later in this talk. That work was about induced universal graphs. I'm going to get to that later. Right, so our main result is that for n-vertex planar graphs, there is a universal graph with a near linear number of edges. And I'm going to be more precise about this leader of one later. So what do we use? Well, obviously, this is a mini symposium about product structure. So as you might guess, we are going to use a product structure, and we are going to use some other tools as well. But let's start with the product structure. So the product structure involves graphs with some bound, with say typically bounded tree width, right? So typically you look at the strong product of a bounded tree width graph and a path. And why do we care about bounded tree width in this context? Well, in this context, we care about bounded tree width because if you have small tree width, you have small separators. More precisely, if you have tree width k, you have separators of size at most k+1. And actually, up to constant factors, having a small tree width or small separators is the same thing. If you have a graph where all the subgraphs have separators of size at most k, then you have tree width at most 15k, right? So up to constant factors, having bounded tree width or bounded size separators is the same thing. And this is really useful because as we have seen, if you have very small separators, then you have small perfectly balanced separators and then you have very good universal graphs with a near linear number of edges. So that's why bounded tree width is interesting in this case. Bounded tree width graphs, they essentially behave like trees. Okay, so we are going to use the product structure theorem. I guess being the last in this session, I don't really have to spend much time on this statement. Let me just quickly recall what it says for planar graphs. It says that every planar graph is a subgraph of the strong product of h times p for some graph h of tree width at most 8 and some path p. I even have the same drawing as Louis in his talk. Okay, so our result is, as you guess, not really about planar graphs, but about the product structure. And what we prove is the following. So this needs to be parsed. We prove that there is a universal graph with a small number of edges. I'm going to get to that. For n-vertex graphs that are subgraphs of h times p, where h is some graph of tree width t and p is a path. But we are not fixing h, right? So for all the n-vertex graphs that are subgraphs of some of h times p for some graph h of tree width t and some path p, there is a universal graph with at most this many number of edges. So what's the bound? Well, there is a linear term in n. There is a term which is n to the leader of 1, but more precisely 2 to the root log n log n. And then there is a dependency on the tree width, t squared, but typically in the applications, the tree width is a constant. So you can think of this as being a constant. Okay, so that's what we prove. So how do we prove it? It would be really out of the scope of this talk to give you a fair account of the proof. So what I'm going to do is I'm going to like fly over the proof like at 900 kilometers per hour. So I'm just going to give you like some glimpse of the ideas that we are using in this proof. The paper is on archive if you want to know more about the proof. But the first thing we do is that we actually clean up the problem a little bit. So there is a subtlety in this setting is that we want to prove something about n-vertex graphs that are subgraphs of this thing, but h is not fixed. H could be any graph with tree width t. And when we build our universal graph, it would be useful if somehow we knew which graph H we are talking about, which fixed graph of T we are talking about, but H is not fixed. Somehow we have to be prepared for any graph of T. So of course here the fix is easy. Instead of like trying to be prepared for any graph H, let's just replace this H by something which contains all graphs of T, all n-vertex graphs of T as a subgraph. That's exactly what a universal graph is good for. And we know how to build good universal graphs for bounded T, right? So that's the first step. You don't have to really look at this slide, but what it says is that first thing we do is that we replace this H, which is not fixed, by a universal graph for n-vertex graphs of T, and that we know how to build using these perfectly balanced separators. So that's exactly what we do first. And then we somehow have to build a universal graph for the n-vertex subgraphs of the product of this universal graph for T graphs. N-vertex graph, okay, let me restart my sentence. Now we are looking at the strong product of this universal graphs for T with a path, and we want to realize all the n-vertex subgraphs in that product. But what is nice now is that we are looking like at one fixed graph. Sorry, we have one fixed graph which has a quadratic number of vertices, and we want to realize all the n-vertex subgraphs of that graph in our universal graph. And that's where the proof really starts in earnest, and that's so everything up to now was some preliminary cleaning, and now we are really going to use the product structure heavily, and we are going to use lots of tricks that are inspired by data structures, and in particular we are going to use a balanced binary search trees. So there will be a vertical binary search tree, and by vertical I mean that it will be a binary search tree on the rows of your product. So like every element, you can think of it as a row or as an element of the path with which we are taking the product. And the role of that BST will be to somehow account for the fact that when you're looking at an n-vertex subgraph of your product, well, we can think of all the n rows in your product, but we don't really know which vertices we are using in each row. And then the weight could be concentrated on some rows, and some rows could be not used. And the vertical BST will somehow allow us to like handle the weight distribution on the rows, and that's so far this is quite standard. But the real novelty in the proof is these horizontal binary search trees, and now we have actually one binary search tree per row. So row 1 has a BST, row 2 has a BST up to the last row, and this is the okay, so there is not much I can say that will make sense in such a short talk. So let me just say that the engine of the proof is what we call bulk tree sequences. And these are binary search trees that are balanced in the sense that they have almost optimal height with respect to the number of elements they contain. And they evolve over the rows. So they start at row 1. They encode some of the elements that we use in row 1, then they go to row 2, some elements disappear, we delete them from the BST, some elements appear, we put them in the BST, and then we rebalance to keep small height. And more precisely, we want the height to be log in base 2 of the number of elements in row I, that's row Ri, plus something which is much smaller than log n at most. And when we rebalance, we want that a vertex cannot move all over the way in our BST. We can control how it moves. So this is really vague, but with all these properties, then we can simulate all that in a construction of a universal graph, and the fact that a vertex cannot move too much when we rebalance, we can actually simulate that by putting only a few edges from a vertex to a next vertex. Okay, really vague. I should stop talking about this proof, but hopefully you have a glimpse of the type of arguments that we use in this proof. So what's the point? Well, we have this near linear bound on the number of edges for universal graphs, for n-vertex planar graphs. And as you've seen, this applies to any class that has this product structure. So if you have graphs on a fixed surface, you have a near linear bound on the number of edges as well, or for k-planar graphs, same thing, for instance. And that's essentially the set of new results for universal graphs. I see that my time is almost up. So I was planning to talk a bit about induced universal graph, but I would say only 2 words then. So there is a related notion of induced universal graphs. And there you want to realize the graphs in your family as an induced subgraph. And now the problem is no longer to minimize the number of edges, but to minimize the number of vertices. And this is not trivial to minimize the number of vertices, because you can no longer take a complete graph here. You want to realize your graphs as induced subgraphs. So you have it's a real problem here. So the question for n-vertex planar graphs was studied for a while. It's also known under the name of adjacency labeling schemes in computer science. And there were a bunch of bounds over the years. Until recently, 2 years ago, an n to the 4/3 bound on the number of vertices was obtained by Bonamy, Gwenaël, and Michał Pilipczuk using the product structure. So they already noticed that the product structure was helpful. And chronologically, that was the 3rd application of the product structure. So the first one was Q-number, second one was non-repetitive colorings, and the third one was this one, if I'm not mistaken. Right, so this was one of the first applications of the product structure. And what we did in this first paper was to get a near linear bound on the number of vertices for induced universal graphs. So the construction is actually different from the one I tried to sketch, but the machinery behind is the same machinery, this data structure of these bulk tree sequences. And one thing we did very recently with Louis and Pat is that we showed that we can actually combine the 2 things together. So there are induced universal graphs with a near linear number of vertices and near linear number of edges. But the construction is more complicated, and there is some blow up in the bounds. But anyway, so it turns out that you can actually combine the 2 problems into one if you want. Okay, so let me quickly conclude with the open problems in this area. By the way, it's a really fun topic. It's really a fun area to work in. So if you're interested to have a look at one of these problems, I really encourage you to. At least I find it really nice. So the first question for universal graphs is, what about if we exclude a fixed minor h? Well, if h is arbitrary, then in general, we don't know better than an n to the 3/2 bound on the number of edges. So if you exclude any graph as a minor, there is a root and separator. So using the stuff from the beginning of this talk, you get an n to the 3/2 upper bound on the number of edges. And for an arbitrary h, we don't know a better bound. I mean, I would guess it's likely that there should be a near linear bound, but we don't know how to prove it without a product structure. And we have no idea how to go beyond product structure. For non-repetitive colorings, there are tricks to go beyond product structure, but here we have no idea how to do it. For planar graphs, well, so we have a near linear upper bound, but there could still be an improvement because for lower bounds, we only have the lower bounds for trees, which is n log n. Right, so this, for all we know, that could be the truth. And there are similar open questions for induced universal graphs. If you exclude a fixed minor h, the best bound on the number of vertices is quadratic. And for planar graphs, again, we don't know what's the right bound. And there, from below, we only have a linear lower bound, not even an n log n. And for trees, for induced universal graphs, this turns out to be the truth. So there is an induced universal graph for n-vertex trees with a linear number of vertices, which is kind of crazy, but that's the truth for trees. And this is much harder to prove than the n log n bound for edges for n-vertex trees. Okay, so let me stop here for this talk. Thank you a lot for your attention.
Thank you very much, Gwen. Any questions? So I'll ask then, what do you think the truth is for planar graphs? Closer to the upper bound or n log n?
But I tend to believe in simple answers, so I would say n log n.
Yeah, I suspect so too.
No idea how to prove that though.
Okay. Last chance for questions. All right, so thank you everyone for sticking with us. It's been a great talk. Thanks, great afternoon. Thanks all the speakers for such excellent talks. Some of you stayed up late to give them, and some of you woke up early to give them. So that's very much appreciated. This has been recorded, and it will be posted to YouTube. If you have an issue with that, please send me an email and we can discuss it. But otherwise, I'll post this to YouTube probably tomorrow. And now I'll stop recording.